right. Hi, guys. Welcome back. This is Scuba Physics Part 2. Yesterday, we went over Boyle's and Charles' Law. We left off with Charles' Law. I want to just quickly review because today I want to start by going over like a small branch of Charles' Law. All right. So Charles' Law states that the temperature and the volume vary directly. All right. So if one goes up, the other goes up. One goes down, the other goes down. They do the same thing. All right. Same thing with the pressure. Well, let's go into that one real quick. All right, so Charles' Law, heat energy increases molecular motion. Let's talk about that. So temperature, real quick, is a measurement basically of how fast molecules are moving. All right, so the higher the temperature, the faster the molecules are moving. The lower the temperature, the slower the molecules are moving. All right, so why do I need to review this? Well, if you have a flexible container, such as like an inner tube filled with air here, what happens is you increase the temperature inside that, you therefore increase the pressure. You increase the pressure, you're increasing the volume. So you're increasing temperature, you're increasing the volume. But it's flexible, so you can increase this volume without a problem. All right, but what happens when you have something like a scuba tank? All right. This is where we have a different branch of Charles' Law. We call it Guy-Lussac's law. The pressure of a gas at a constant volume, okay, steel tank, constant volume, is directionally proportional to the temperature. All right. So what this means is you heat the tank. If you leave this steel tank out in the sun, okay, the molecules inside the scuba tank are going to start to move faster and faster. And since the volume cannot change, it can't expand, you're going to increase the pressure instead. And if this continues to happen, you continue to heat this up. Okay, what will eventually happen is since that steel tank will eventually crack and can explode, and that's cause a big problem. That's why most scuba shops, when they fill up an air tank, and you should get somebody certified to do so, they're going to put it in a tub of water because the water is going to absorb some of this heat as you're adding air to the tank. And if you absorb the heat, you should be able to keep that pressure under control so the tank doesn't explode. All right. All right, next slide here. Now let's talk about Dalton's law. All right, so Dalton's law. The total pressure exerted by the mixture of gases is equal to the sum of the pressures of the gases making up the mixture, with each gas acting as if it alone was present and occupied the whole volume. Guys, the easier way to remember this is to say that the sum of the parts equals the whole. What does this mean? This means if you have a mixture of air, which we now should know is nitrogen, oxygen, and carbon dioxide, mostly, that each of those gases is exerting its own pressure. When you add that together, it equals the total pressure. All right, so another example. All right, so here, I'm not going to be using moles too much because it's not chemistry class, but this is a good example. Okay, so we have two separate gases. We have hydrogen and we have helium. In one container, it's just hydrogen. We have 0.6 moles of hydrogen. The second container, you have 1.5 moles of helium. We're using moles as a measurement of pressure. When you add these two together, they equal 2.10 moles of gas. That's the total pressure for this container. And notice it's at the same level. Another example, let's see. All right, let's talk about partial pressures of air in a scuba tank. All right, so if you're at sea level, we now know that 14.7 psi is equal to 1 atmosphere. Another measurement of pressure we use is 1 bar. 1 atmosphere is equal to 1 bar, or 14.7 psi of pressure. Okay, and every 33 feet of seawater you go down, you add an extra 14.7 psi, 1 atmosphere, or 1 bar. All right, so what we're going to look at here is the two main gases we're concerned with in scuba diving in your tank of air. We have nitrogen and we have oxygen. We know that nitrogen makes up 79% of what you're breathing. And oxygen makes up about 21% of what you're breathing. So if we talk about the pressure, we're trying to get this to equal 1 bar, 1 atmosphere. And for my class, that's the easiest way to measure it. Okay, well, 0.79 plus 0.21 atmospheres equals 1. Okay, so all you have to do is add 0.21 atmospheres. I know it doesn't say ATM here. And 0.79, and you should end up with 1. All right, so that's at sea level. That's the partial pressure, pp, partial pressure of oxygen and nitrogen. Now, when you move deeper, we're going to combine a little bit of Boyle's law here. As you move deeper in the water at 33 feet, okay, remember 33 feet is a total of 2 atmospheres. Because you have 1 atmosphere. Not very good at this drawing thing here. All right, you have 1 atmosphere of air above you and 1 atmosphere of seawater above you. So 2 bars or 2 atmospheres. Sorry, my dog decided to get up at that moment. All right, so at 2 atmospheres, that means you have 2 times the pressure of oxygen. So 0.21 times 2 is 0.42 atmospheres of oxygen and 1.58 atmospheres of nitrogen. That's just double what you had before. But if you add these together, 0.42 and 1.58, they should give you 2. All right, same thing if we go down to 66 feet or 33 atmospheres of air. We're trying to add up to 3 bars or 3 atmospheres. You take what you had at the surface, 0.21 atmospheres of oxygen should give you 0.63 atmospheres of oxygen at 66 feet. 3 times 0.79 should give you 2.37 atmospheres of nitrogen. And these both then add up to give you 3. All right. Now, why is this important? Why do we care about what the pressure of oxygen and nitrogen we're breathing? Well, it's actually very important because of something called Henry's law. Hey, girl. All right, Henry's law. So Henry's law states, let's see here. Henry's law is the amount of any given gas will dissolve in a liquid at a given temperature is proportional to, so directly proportional to, the partial pressure of the gas in equilibrium with the liquid and the solubility coefficient of the gas in the particular liquid. In other words, an increase in pressure, sorry, my star's not right here. An increase in pressure will increase absorption. You increase the pressure of a gas, you're going to increase how fast it dissolves into your bloodstream, into a liquid. Okay, this has to do, last chapter we talked about the atmosphere in the ocean. Well, if you increase the pressure of carbon dioxide on the ocean by adding more carbon dioxide to the atmosphere, it's going to end up dissolving into the ocean faster. Well, now when we're scuba diving, what liquid are we talking about? You'd think seawater, but the main one we're concerned about is blood. Okay, your blood. We are concerned with how much gas is dissolving in your blood. So if we increase pressure, more gas is going to dissolve in your blood. Well, when it comes to things like oxygen, that's not such a bad thing. That can be later on, but initially it's not such a bad thing. Extra oxygen, extra energy, you're going to feel great. All right, but when it comes to nitrogen, when you add extra pressure of nitrogen, that can be a problem. All right, so here's what happens. You have your tissues at 1 atmosphere here. All right, 1 atmosphere, your tissues have the same amount of gases, let's say nitrogen and oxygen, as your lungs. They're in equilibrium, all's well. As you increase, you breathe through your scuba tank, you're adding in extra air molecules. And these air molecules are going to want to travel into your tissues. You have an increase here, so they're going to diffuse into your tissues. Okay, until your tissues reach equilibrium. All right, so not necessarily a problem if you're at depth, we've got equilibrium going on, but here's what happens as you decrease pressure. So we've increased pressure, we're increasing the amount of gas that's dissolving into our bloodstream, which then goes from the blood into your tissues. Well, as you decrease pressure in your surface, what happens is all this gas that's been dissolved into your tissues is going to need to come out of solution because it's going to do the opposite. You increased what was absorbed, now you're going to have these gases start to go back into your blood and they're going to precipitate out. Well, they're in your tissues. This is where we need to do something called off gas. We need to give it time. We need to slowly decrease the pressure so that these gases can go back into our blood and precipitate out slowly. What happens if they don't precipitate out slowly is that you form bubbles, and in particular, nitrogen. Okay, nitrogen is the dangerous one. Nitrogen, you breathe in a whole lot of nitrogen. If you don't give it enough time, nitrogen will go back into your blood, okay, but it will bubble out. And if it forms bubbles, it usually collects in areas of your joints, and we call this the bends, which is, I think, this next one here, Bert's law. Pressure can be reduced by half or less without a gas coming out of solution. So you can reduce the pressure by half. Okay, this is why you go up slowly from depth in order to reduce how much precipitates out. So think of a soda can for a second. Another great example before we get to the body is a soda can, all right? So when you pack a soda can, you increase the pressure. They're pumping a whole bunch of carbon dioxide into the soda can. They're increasing the pressure. They quickly seal it to keep that pressure down. So, and what they're doing is when they keep that pressure down, you're keeping the gas dissolved. As soon as you open that soda can, you hear a fizz. All right. If you shake that soda can, you get more than just a slight fizz. You get a whole bubbling up. What happened? Well, when you shake it, you increase the gas molecule motion, you increase the temperature, you increase the pressure. You increase the pressure, you open it back up, guess what happens? Out comes all the gas. All right. And that's where we have problems with nitrogen. Your body's kind of like a soda can underwater. You increase the pressure, gases dissolve in, no problem. But if you surface too quickly, like shaking up that soda can, all the bubbles are going to come back out. All right. We are going to pause here, and I will do part 3 tomorrow. We'll get to Martini's law in a little bit. Actually, you know what? We'll go on real quick. So Martini's law, this also has to do with the bends and everything. This one's actually called nitrogen narcosis. Let's see. Nitrogen, I can't spell it. Anyway, with my pen, take too long here. But nitrogen narcosis, or Martini's law. So nitrogen that's absorbed under pressure can have a narcotic effect. So we said oxygen is not such a problem. We'll get to oxygen later. But nitrogen absorbed under pressure has a narcotic effect. Okay, it's kind of like being drunk underwater. So the deeper you go, the more nitrogen, according to Henry's law, is dissolved into your bloodstream. So it's kind of like drinking more and more alcohol. Okay. And it'll start to affect your brain. This is not a permanent thing. This is not like the bends. This is not a permanent thing. All you have to do is come up a little bit, maybe an extra atmosphere, and that nitrogen dissolves kind of out, and you don't have such a horrible narcotic effect. But they call it nitrogen narcosis because of the narcotic effect, or NART at any depth, for no reason. Usually it's past 100 feet, everyone is NART, is what they say. All right. You'll do crazy things like hopefully not murder your dive buddy, but it's possible. You might start doing somersaults underwater. That is not me, but I have seen people do that. Actually, my younger sister did that once. I thought she was just having fun, but turns out she was a bit narked because then she pressed, we called it the elevator button, but that's another story. She pressed her BC and started shooting up to the surface past 100 feet. It was a problem. Good news was nobody was harmed, but ask me in class. I'll tell you the full story. All right, so that's being narked. Also has to do with nitrogen, but it's not the same as the bends. The bends is the nitrogen bubbles, can cause more permanent damage. And I think that's all I have time for now. Stay tuned. I think tomorrow I might give you part 3 of scuba physics. All right, bye for now.